Hi, I want to talk briefly about applying Newton's second law to situations where an object's turning. Now, in Chapter 4, when we talk about motion in more than one direction, we said the framework that we can use to thinking about motion is thinking about motion for a system that's either purely turning or a system where the speed is changing and the direction is changing. Rather than trying to separate things into just a Cartesian x-coordinate and y-coordinate, we could use a direction where the direction of the current velocity is one of our components, and a direction representing the radius of the curve that an object is currently traveling in represents the perpendicular direction that we are experiencing. So for the case where the speed is constant, we said the size of that acceleration would have to be equal to the speed squared divided by the radius of the turn, and we call that type of acceleration a centripetal acceleration. And centripetal is a word that means center seeking. So if the radius is from the center of the turn to where our object is, the direction of the centripetal acceleration would be in the negative r hat direction, directly in towards the center of the turn. Now, if the speed is changing and the direction is changing, we said we also had a translational or tangential component to our acceleration that acts along the current direction of the speed, what we call the current direction of the velocity, what we call the v hat direction. And v hat and r hat are, as I said, perpendicular to each other, so these are independent 90-degree differentiated vector components. Now, in order to be able to cause that acceleration, we apply Newton's second law. And Newton's second law says we get an acceleration by looking at the sum of the forces, the net force acting on an object, and dividing by the translational inertia, the mass of an object. Now, if we have purely centripetal motion, what we call uniform circular motion, then what we need is a constant force, and we need a force that is capable of turning as that object turns. So one example, if you're whirling a mass on a string, then there's a force of tension all along that string, where that tension from the object that's whirling is always pulling in towards the center. Another example of an object in nearly circular motion, if you look at the moon orbiting around Earth, there's a force of gravity between the moon and Earth, and that force of gravity is always pulling the moon towards Earth. But because the moon is moving, it keeps changing the direction of the velocity, and as the moon keeps moving, the direction of the force always points towards Earth, so you have a situation where you have nearly uniform circular motion. So, as long as you can have a force that's capable of turning, a force that can rotate with an object, we sometimes call that force a centripetal force. It's like the net force isn't a new force, it isn't its own separate thing. Net force just means like net pay. We add up everything in the positive direction, take away everything in a negative direction, and what's left over is what we have to work with. So centripetal force is really net force for turning. As long as we have some uncanceled component of force that continuously changes direction, then it would give us an acceleration based off the principles of centripetal acceleration from Chapter 7. Speed squared divided by the radius is the acceleration, times the mass of our object is how large that centripetal force needs to be. And if we had a more complicated acceleration, then our force would have to have a centripetal component and a component in the direction of the motion. And we'll take a look at some more complicated applications of forces as we get into a better framework for talking about motion that has purely rotational components as we get into chapters 10 and 11. Thanks for watching.